Should have put all that on video as well. The importance of this unit. Angle measurements. So this particular day is angle measurements and coterminal angles. Angles can be measured using two different units. One of them you're super familiar with. What do you normally measure? An angle is like how wide the opening is. Degrees. Degrees is the one you're pretty familiar with. Right? If I ask you to draw me a 45-degree angle, most of you would draw it, accurate within 2 or 3 degrees, even freehanding it. If I ask you to draw me something in radians, you'd probably have no idea what I'm talking about. And that's okay, because we're just starting. It's a little bit like when you first learn about meters in science. You're like, oh, meters, nobody knows what meters is. And then later you're like, oh, that's all we use, because it's a lot easier. It's very similar. Right now you're like, radians, nobody does radians. And by the end of this unit, you'll be thinking, nobody uses degrees, let's use radians all the time. And we will use radians all the time, by the way. Radian units are very convenient for a variety of reasons. We'll talk about those reasons in a little bit. In calculus, we use radians exclusively. That doesn't need an explanation point. We use radians exclusively. We don't use degrees at all in calculus. You can put your calculator in radians and leave it there in calculus. The derivative rules and integral rules only work if the angle is in radians. That's more for next year. But that's just to say that, yes, radians feel weird initially, but eventually you will prefer them to degrees. Converting from degrees to radians or radians to degrees. This was my favorite part of chemistry. I don't know why people don't like this part of chemistry. When you're converting things, because you don't even have to understand the chemistry. You just make sure the units work out. And stoichiometry, yes. It's all math. That's probably why I liked it, because I didn't need to know the chemistry. I could just do the math. And so maybe some of you are like that. Maybe some of you didn't like that. But if you make the units work out, you kind of don't have to understand what's going on. I feel like that's how I survived college chemistry, is make the units work. I don't understand what's happening, but I got enough to get through. How many seconds are in a year? I don't know. 1 year. Let's start with that. See what happens. Railroad tracks. Let's see. So I want years to cancel, so I'll need a year in the bottom. And 1 year has 365 days. I'd like to get to seconds, though. So I need my days to cancel. I don't know how many seconds are in a day, but I do know how many hours are in a day. 24 hours in 1 day. Then I'd like my hours to cancel. Some people know how many seconds are in an hour. We can skip a step here.
60 minutes in an hour. 3600.
Careful.
3600.
So 1 hour has 3600 seconds. And to get the 3600, you just did 60 times 60, which is what the longer way to go would be. Okay, so years cancels, days cancels, hours cancels. We're left with seconds. And this test is going to be no calculator, but we're also not going to ask you to do 365 times 24 times 3600. That's a lot of seconds in a day, or in a year. 31,536,000. But we did that example to say that it's going to be the same thing with degrees and radians. It's going to be easier. 5,280 feet in 1 mile. Convert 30 inches per second. Okay, so we got a top and a bottom to deal with here. 2 miles per hour. I'm just curious. Survey. How many of you liked this part of chemistry? The stoichiometry part. Any of you not like this part of it? Okay, that's fine. Half and half. Again, I liked it, but I know why I liked it, because it was all math. Let's see, inches. I want the inches to go away, so I need the inches in the bottom. I'd like to get to miles, but I don't know how many inches are in a mile. I do know there's 12 inches in 1 foot, though. And then I would like my feet to go away. Well, not my feet, but you get the idea. I'd like the unit feet to go away. 5,280 feet in a mile. So, and I'm not done, but I'm going to just kind of check and make sure. I've got my miles ready to go. So if I stopped here, I'd be miles per second. But I want miles per hour, so I need the seconds to go away. And I can turn them straight into hours. I know there's 3,600 seconds in 1 hour. So 30 times 3,600 divided by 12 divided by 5,280. 245.45 mph. Our problems are not going to be like this. It's just to remind you that you've done this thing before, stoichiometry stuff. Now we're going to use it with radians and degrees. Whatever that was.
Some more lights for everyone.
Alright, so let's go 45 degrees to radians, but here's our, I'm going to blow past the key part of the day here. Pi radians. Alright, pi is 3.14, you're familiar with pi. Pi radians is 180 degrees. Pi radians is 180 degrees. Like that's the summary of today. Like I should just box that in and walk away and you'd be good for today.
Cool.
Today's notes in 5 symbols there. So let's convert, but now let's do a little practice for that. Make sure we can handle this. 45 degrees to radians. So I want degrees in the bottom to cancel out the degrees in the top. And one's a symbol and one's a word, but that's fine. They're both degrees. So 180 degrees is pi radians. And unlike the chemistry stoichiometry where it's, stretches across the page, this is just a one-step deal here. Degrees cancel, leaves me with radians. 45 pi over 180. I feel like, no, we don't want a calculator. I don't want to know what that is in decimals. I want it in terms of pi.
Quarter pi.
A quarter pi. That's true. We don't ever phrase it that way. That's
Pi.
That's absolutely right. We would say pi over 4. But yes, quarter pi is correct. We would say pi over 4. I've never heard quarter pi. It's not wrong though.
Now you have.
Now I have. All right, why don't you convert negative 50 degrees to radians? Number 3. Going the other direction. Converting 5 pi over 6 to degrees. Now, this is a little bit strange maybe. There's something subtle that just happened here. 5 pi over 6. How do I know that that's radians? Like, it didn't say 5 pi over 6 radians. Well, it's not in degrees, so it must be in radians. That would be an answer.
It's asking for degrees.
It's asking for degrees, so I must be starting in radians, because those are the only 2 things we know about. There's a pi in there, and that usually means it's in radians. Those are all good answers. There's a better answer coming up, but we'll stick with those for now. So 5 pi over 6 radians. So I want the radians to go away. Pi radians is 180 degrees. So the radians cancel. The pi's cancel.
5 times 180.
And 5/6 of 180. Well, maybe 180 over 6 would be a better way to go. 180 divided by 6 is 30.
Times 5 is 150.
Times 5 is 150. So 150 degrees. Why don't you try the next one? 180 divided by 3 is 60. Times 5 is 300. And that answer is intentionally slightly wrong. Negative. Sometimes people will forget the negative because I guess they get so involved in the conversion and the canceling and the simplifying that they forget about the negative. Michael?
If it's a circle, wouldn't like negative 300 degrees be the same as 60 degrees?
Yep. Hold that thought. We're going to get there in 5 minutes. Yep, you're absolutely right. All right, if you write an angle measure in degrees, you must use the degree symbol. Or you could write degrees, but why would you write out degrees when you could use the symbol? You got to do something to say you're in degrees. If you write an angle in radians, you do not need to write radians afterwards. It's understood, and it is understood. The reason it's understood is here's the definition of radians. So there's a piece of a circle, a slice of a circle. Theta in radians, so that angle in radians is the arc length divided by the radius. Yeah. But SOHCAHTOA is with triangles. This isn't a triangle. That's a piece of a circle. So it's not opposite over adjacent because it's not a right triangle. But look what would happen. Length would be in inches and radius would be in inches. And so the measure of that angle doesn't have a unit. So more than like just discarding radians because we don't like it or we don't want to write it or we just understand it, it's like radians is a unitless unit, if that makes sense. Because of its definition, a degree in radians is a ratio, and therefore it doesn't even have units. So you can put radians on there if you want to, but radians just means you're measuring angles. It doesn't really have a unit. It's kind of weird, but that's why you don't have to put radians. There is no abbreviation for radians since we don't write the units for radians. Radians is a unitless degree measure because it's a ratio. Lots of stuff we could go with that, but we'll stop there. All right, since we work exclusively with radians in calculus, we've got to have a good understanding of like how big they are, where they are, how does it fit on the circle? What about those key angles? And again, you're pretty good with this. I probably could have left that blank and had you fill it out, and you would all got it right within a couple minutes because you're good with degrees. So you do need to know that, but we also need to know how to get the same picture in radians. Now, let's go kind of an organized fashion here. When we measure an angle on the circle, we start at the positive axis and measure counterclockwise. So we start at 0, that's easy, whether it's degrees or radians. And we said that, what was our main conversion factor for degrees to radians? What's equal to pi though? 180. So I can come over here to 180 and I know that's pi. So if you can remember that pi equals 180, you can pretty much figure out the rest because halfway between 0 and pi is right there, and that'd be pi over 2. So I'm not going to fill these in order. I'm going to fill them in sort of a logical sense to me. What about halfway between, wait a minute, we need to know what's all the way around. 2 pi. Little side note, what's the circumference of a circle? Well, that's the angle measured all the way around. What's the formula for the circumference of a circle? That's the formula for the area of a circle.
2 pi r.
2 pi r. All the way, you got there, that's right. All the way around the circle is 2 pi. All the way around the circle is 2 pi times the radius for the length. What's halfway between 1 and 2? 1.5. Now, we don't usually write 1.5 pi. That wouldn't be wrong, but that's not how we write it. We write it as 3 pi over 2. They're all going to be fractions. Okay, so we got our quadrant markers. The official name for those is quadrantals. They sound fancy. The quadrantal angles. How about halfway between 0 and pi over 2? Pi over 4. Right? Half of a half is a fourth. Especially if you play a sport that's divided into quarters. Half of a half is a quarter. What about halfway between pi over 2 and pi? 3/4 pi or 3 pi over 4. 3/4 pi. 0.75 pi if you want to be weird about it. Okay, a little bit trickier here. Halfway between 1 and 1.5.
3/4?
It's a fourth, yes. How many fourths is it? Yeah, 1 and 1/4.
1 and 1/4 pi.
But we go with 5 pi over 4. It is 1 and 1/4 pi, 1.25 pi, but we don't ever use those. We use the fractions. How about halfway between 3 over 2 and 2? Halfway between 1.5 and 2?
7 pi.
Let's see. Or, here's what he might be doing, and here's what you'll switch to doing. You can count by pi over 4s if you'll count by 45s. Pi over 4, that's 1/4. 2/4, 3/4, 4/4, 5/4, 6/4, yeah, 7/4, and 8/4. And then of course we reduce them each time. Alright, this first one is probably the trickiest. After that we can count our way around. 30 degrees is, I'm going to just do the conversion out here to the side, is pi over 6. Now you can do the conversion for every time, for every spot on the graph, but that's like 16 conversions. So there's got to be a better way than just multiplying by pi over 80, pi over 180 every time around. Ignore the middle markers if you can. Like ignore the pi over 4s or the 45 degrees. I'm not getting this to call on anybody. I'm getting it to cover up the 45 degree markers, and the rest of those arrows are all 30 degrees apart. You good with that? 30, 60, 90? Which means they're all pi over 6 apart. So I can count, cover that up even more. I can count by pi over 6. So this one's 1 over 6. This one's 2 over 6. But I'm not going to write 2 over 6. That's pi over 3. Okay, I'm going to back up and start over again because I lost track of where I was. 1 over 6. 2 over 6. 3 over 6. Yeah, that's right. 4 over 6, also known as 2 over 3. I didn't lose my place, but I'm going to pretend I did so I can count again. 1 6, 2 6, 3 6, 4 6, 5 6. 6 6. Fine, that's there. 7 6. Not looking at that one. 8 6, also known as 4 pi over 3. 9 6, which is 3 pi over 2. 10 6, I'm really getting, that's 5 pi over 3. What was that? That was 10 6. Here's 11 6, and I end at 12 6, also known as 2. Soon enough, not now, not yet, but soon enough you'll have those, you'll be so familiar with them, you'll have them memorized, not because you intentionally memorized them, but just because you worked with them so much, you just know them. That's the goal. There's also lots of patterns going on, and we'll start to look at them now. Like, look at all the denominators of 6. There's all my 6 denominators. It's like there's some kind of symmetry going on. All of those are the shallow angles, right? In their respective quadrants, they're all shallow angles. Maybe we should have started with the 4s, because those are, I think, even more obvious. By the way, it's nice to have 3 colors of highlighters. And share with your neighbor. It doesn't matter what color you pick. I just like to put all the over 6s one color, all the over 4s one color, and they're all in the middle. So all the 6s are the shallow angles. All the over 4s are the middle angles. And then if you highlight all the over 3s, all of those are the steep angles. So every quadrant has a shallow, middle, and steep. And the shallow is always the over 6, and the middle is always over 4, and the steep is always over 3. And there's a whole lot more patterns going on, but we'll stop there for now. So, especially when we get to sines and cosines, you'll start to notice lots of different things. So for now, I don't know that I would say memorize that. You're going to become so familiar with it that it doesn't take memorizing. Plus, it's easy enough to do it, to fill it out just like we did. As long as you know that pi is 180, you can fill that in, and after that, you can just figure it out. Okay, I'm going to let Michael teach the rest of the lesson, because coterminal angles, coterminal, what's co mean? Like together or same, or with, like cooperate or cohabitate. You're doing stuff together. What's terminal mean? End. That's right. I mean, yes, the nice example is the airline, the flight ends at the terminal. Right. The darker example is a terminal disease means that the end is coming, like that's the end. All right. I mean, it's not fun to talk about, but that's where the word terminal comes from and what it means. I heard her. Yeah. I mean, terminal cancer or terminal whatever means end. Okay, so a coterminal angle means an angle that has the same end, same landing spot even, if you want to go with the airplane analogy. Let's back up a little bit here. The initial side of an angle in standard form is always at 0 degrees. So you always start on the positive x-axis. That's another way to say that. 0 degrees is the positive x-axis. And the terminal side, the ending side of an angle, is the side formed by rotating a ray from the initial side. That sounds complicated, but rotating it up. So there's an angle. That angle might be pi over 4. I drew it kind of right in the middle, so maybe that angle is pi over 4. One complete revolution is 360 degrees. You guys mentioned that earlier. That's equal to 2 pi, so that'd be all the way around. Graphically, this was Michael's question earlier, there's no difference between a 45-degree angle, which is also what I drew, and a 405-degree angle. Because a 405-degree angle, I'm going to do a different color, would mean you'd go all the way around, that's 360, and go 45 more. So there's your 405-degree angle. But they land at the same spot. They are coterminal. So this gets to be a little bit weird, because in the XY plane, there's no way to land at one spot two different ways. Like, if the coordinates are 1, 1, it's the only way to get there. Here, if you want to land at pi over 4, you can say, well, I could go 45, or I could go 405, or you sort of mentioned it earlier while we're here, you could get real creative and go backwards. How much would that be?
360.
But I'm not going backwards all the way. And it needs to be negative because we're going backwards. So here's a question for you. How many ways are there to land at that particular angle? Infinite, because you can spin around as often as you like. To find coterminal angles, then, what do you think? You guys are almost... What's that? Say it again?
Hope and pray.
Hope and pray. How do we get from 45 to 405? What did we do to... So you could add or subtract 360 degrees as many times as you would like. So you could add 360 and then add 360 and then add 360 and then add 360. Now, we're not usually in degrees, we're usually in radians. So in radians, we would add or subtract. What's the equivalent of 360 is 2 pi. As many times as you want. Side note, this would be a reason we give multiple choice test, because if we give an open-ended test and ask you on number 5, write 6 coterminal angles for 30 degrees, make 3 greater than 30, make 3 less than 30. Okay, so I can add 360, and that gets me 390. There's one of them. If I add 360 again, let's see, that would be 750. And if I add 360 again, oh, I've got to carry the 1 this time, so 1110. So there's 3 coterminal angles with 30 degrees. The reason we make it multiple choice on the test rather than open-ended is because some of you knuckleheads are going to tell me that a coterminal angle is that. Do you believe that? Because I went, 360 times 10,000 plus 30 degrees. So that is 10,000 revolutions plus 30 degrees. So yes, that is coterminal. And that's not bad, because I can tell by looking at what that is. What students like to do to jack with their teacher is to do like 360 times 179. But of course not show the work. Just do that out to the side, add 30 and box that answer up, and force me to figure out, I don't know, is that or is that not? I've got to go do some work to figure out if it works or not. The people that are smiling are the ones that would be doing it probably and enjoying it. 3 more, but less than 30, so 330 minus 360 would be negative 330 minus 360. I sure hope there's not an open-ended problem on the test now, because because I'm going to get that from some of you. Fortunately, I know how to find out if it works or not fairly quickly from dealing with troubled students for 20 years. Let's see, negative 1050. Number 6. Write 6 coterminal angles for negative pi over 6. Make 3 greater than negative pi over 6, 3 less than pi over 6. So, a little bit harder maybe. So I want to add 2 pi. Uh-oh. What is this going to require? How do I add fractions? So, you know what? I'm just going to kind of start over and say, instead of adding 2 pi, I'm going to add, well, it's still 2 pi, so I should be careful how I phrase that. I'm going to add 12 pi over 6. Because that is 2 pi, it just has a common denominator. So that's 11 pi over 6. There's one answer. And I'm just going to keep adding 2 pi. Except I'm not going to write it as 2 pi. I'm going to write it as 12 pi over 6. Because I don't want to keep converting to a common denominator once I know what I'm doing. So 23 pi over 6. Add 12 pi over 6 again. 45 pi over 6. But did I do that wrong? I did do that wrong. How about 35 pi over 6? And again, the enterprising, mischievous pre-cal student could do 12 pi over 6 times whatever integer they like, add it to negative pi over 6 and give me some weird answer and force me to figure it out. So there's greater than negative pi over 6. We want 3 less than negative pi over 6. So instead of adding 2 pi, let's subtract 2 pi. So negative 13 pi over 6. Try not to mess this one up. Negative 25 pi over 6. Negative 37 pi over 6. Dot, dot, dot. I could keep going as many times as I would want to. And again, the whole point is that all of those angles, let's see, negative pi over 6 would be backwards 30 degrees, would be right there. The rest of them would land right there. They would just get there going crazy ways, like all the way around, backwards, and then a little bit more. Or forwards 3 times, and then, they all land at the same spot. They're all coterminal, same ending. All right, next question's a little bit weird. In which quadrant does 50 pi over 3 lie? Like, I don't know. That's 50 pi over 3, that's a lot of times spinning around. Okay, if you convert it to degrees, I don't want to do that. I want to do this in radians. And I'm going to use the coterminal idea. So I could subtract 2 pi and I would land at the same spot. And it would be much easier to figure out where a smaller angle is. So I'm going to subtract 2 pi. And again, I need a common denominator. So I'll subtract 6 pi over 3, because that's the same thing as 2 pi. That's 44 over 3. I don't know, that's not particularly helpful. I don't know where 44 over 3 is either. So what could I do?
Subtract another.
Keep subtracting 2 pi until you get something that you like. So 38 pi over 3, no. And at some point you don't have to write them out, you just start subtracting 6. 32 over 3, 26 over 3, All of these are coterminal angles, but I'm getting it down to a reasonable. Did I mess something up? 38, 32. Because I'm subtracting 6 each time. 14 over 3. 8 over 3. Maybe some of you would stop there and be like, I can figure out where 8 over 3 is.
2 pi over 3.
And if you do stop there, probably the only reason you stop there is because in your brain you think that it's 2 pi over 3. Okay, so where's 2 pi over 3? Let's see.
Second quadrant.
It's definitely less than pi. How does it compare to 1/2?
Greater.
It's greater than. Or I could remember that the pi over 3s are the steep ones, and 2 pi over 3 is in the second quadrant. Quadrant 2. Or a lot of times we use Roman numerals for quadrants. Be fancy. Alright, so I feel like it's not a difficult concept today, but it's a super important concept today, is being able to convert, so like knowing what those key angles are in radians. And then the idea of coterminal is add or subtract 360 as many times as you want to frustrate Mr. Wolf, or add or subtract 2 pi as many times as you like.